So hello everybody. Yes, please do interrupt me if you have any questions. That would be much appreciated. And thank you very much for the opportunity to speak. I'm going to start by just saying how sorry I am that I can't be there with you. I was really looking forward for this meeting. Unfortunately, the situation back home is a little bit complicated. But I hope yeah. Anyhow, I'm sure you all are talking about very interesting things and so I'm going to talk a little bit about this notion of electromagnetic duality. I'm going to use to some extent the framework of ambidexterity to do it, higher semi-additivity. I already gave a few talks about this higher semi-additivity in general in these collaborations, and I think there's a lot of people who heard, let's say, a basic introductory things, at least from me, about this. So I'm not going to be as introductory specifically about that this time. But if there's something that is unclear and you want to ask, just ask me, and I'll be very happy to clarify um, as we go along. Okay. So so the idea we're going to start with a basic mathematical phenomena that you all know very well. And I'm going to call this phenomena the discrete Fourier transform. But what it's going to be is really an isomorphism of commutative rings. So here it is. So let's say we have A is a finite abelian group. And a dual is how I write the Pontry eigendual. Then I can consider the group algebra of A. And this algebra as a commutative ring is isomorphic to the ring of functions on the dual group. Note that when I write this symbol here on the right, I just think about the dual group. The dual group is, of course, a group, but I think about it as a set. So it just means it's a complex valued functions on this set, this finite set. And here I'm taking the group algebra. And I would claim that this isomorphism is in some sense the content of the discrete Fourier transform. This understood.
A is a P group, is that right?
No, just a finite abelian group.
So you've already used both the complex numbers and QP?
Oh, I'm sorry. Of course, I wanted to say Q mod Z. And in my head, immediately. Thank you. No, Q mod Z. I'm sorry. Thank you very much. Yes, but of course, very soon we're going to think about P, things which are more P primer. So, so we can ask, if we look at this kind of isomorphism, I want to ask the following question. Well, this is an isomorphism of commutative C algebras. So here's right. So this is a commutative rings under C, and I'm going to be, I'm going to make a big point about saying that commutative rings under C, that's the same as commutative algebras in C vector spaces. So if you have the category of C vector spaces, it has a monoidal structure given by the tensor product, and commutative rings are just commutative algebras in that category. So, and what I want to start thinking is trying to meditate about the question, what did I need from this category of C vector space to have this kind of an isomorphism? Well, there's a few things that we can observe. So, for example, we can observe that if I go or if I replace C, for example, by Q, and I add all roots of unity, so the maximal abelian extension, such an isomorphism is still true. So we don't need our field to be as big and as algebraic closed as the complex numbers. So we can already get this kind of a Fourier transform isomorphism in commutative algebras in Q adjoint roots of unity vector space. We can also see that you might say, well, what about can I go all the way to Q, for example? If we're playing the game of getting my fields smaller and smaller, what about Q? But that is not going to be true. For example, it is not true that if we look at the group algebra of the group Z mod free, this is not going to be isomorphic. So something is needed. We can also ask, well, let's say that we want this isomorphism to hold. So we see Q is not enough. So we can get it to hold, but we don't need to add all roots of unity in the world. We just add a primitive 3 roots of unity. That is already enough to get this isomorphism. And maybe last, we can say, well, did we really need to work over the rationals? Like, what would happen if we just work over the reals? Over the integers, and add a primitive roots of unity? So then the isomorphism is not going to hold. But it is going to hold once we invert free. So if R is Z adjoin free, invert free, it is going to be true that we are going to get these isomorphisms. So in some sense, if we're interested in this Fourier transform isomorphism for the group Z mod free, we get that this ring is in some sense the minimal possible ring we can work over. But maybe we can do even less than that. Maybe working with commutative rings over maybe looking at modules over rings is already too specific. So let's really try to understand what is the minimal data required to construct this map of the Fourier transform and get it to be an isomorphism. So that's what I want to understand now. And all abelian groups are built out of cyclic groups. And so I'm going to, and cyclic groups also decompose to p primary cyclic groups. So I'm gonna concentrate on the case when we're thinking about something of the form R Z mod p to the k versus R Z mod p to the k star. And I want to talk about this in larger generality. So let me do this. So now I'm going to replace R mod by some symmetric monoidal category, C. And they're going to assume that I'm also going to allow myself infinity categories for later. So what are those two rings? How should I think about the two rings on both sides? Is there a way to write them down in a completely categorical manner? So if I have a symmetric monoidal category, then it admits a unit. And if I think about my ring R in the world of R vector spaces, that's the unit. And if I look at both of those rings, they look like the underlying object look like a direct sum of finitely many copies of my unit. So it already seems to be necessary to assume, or reasonable to assume, that my category admits finite coproducts. So I'm going to assume that it admits finite coproducts, because otherwise, even ignoring the ring structure, I can't even write those objects. Now, if I have such a category, among all infinity categories that admits finite finite coproducts, there's an initial one, which is the category of finite sets. So there exists a unique symmetric monoidal functor from the category of finite sets to C, which preserve finite coproducts. And it sends, well, what is it? It's symmetric monoidal, so it has to send the point to the unit. And it's coproduct preserving, so it has to send set A to A many copies of the unit. Okay. Now, because this functor is symmetric monoidal, it sends monoids to monoids. So if I consider a finite group A, I can think about that as a commutative algebra in finite sets. And my functor, this functor, let's call it, I'm going to denote it like this, unit C bracket A, is going to go to a symmetric, is going to go to a commutative algebra. This is the free algebra. That's the group algebra construction. So every time that I have a symmetric monoidal category, and it has finite coproducts, I can think about the notion of a group algebra in that context. What about this other side? Well, this doesn't use the structure of A star as a group. It's only use it as a set. I just want to be able to take the product of my unit A star many times. So I'm also going to assume that my category admits finite products. I'm also going to assume that it admits finite products. So my goal is then to construct the Fourier transform map from the unit adjoint Z mod P to K to the unit adjoint Z mod P to K star. Okay. Now it's not hard to see that this is in fact, so okay, let me add a condition that we can remove later. For simplicity, instead of going over the existence of this finite coproduct, let's assume that C admits that C is presentable. So I'm going to assume that it admits all possible colimits. We're going to remove this assumption later, but it will allow me to make all kinds of arguments using adjoint functors that otherwise I will have to do a little bit locally. If this is the case, then I can upgrade this functor from finite sets to a functor from the infinity category of spaces. That is the free infinity category that admits all colimits. Under this structure, I get that this functor is part of an adjunction. So the free group construction, the group algebra construction is in fact a left adjoint. So this is the same is formation as a monoid map to the monoid of home from the unit of C to the unit of C Z mod P to K star. This is just a fact. This has nothing to do with this guy here. This is the universal property of the group algebra. Mapping from the group algebra is like mapping the group into the home from the unit. Now, here I'm just computing a limit, so I can take it to the outside. So I get a map from Z mod P to the K times Z mod P to the K dual. I need to give a map from this to a home from the unit to itself. Again, a monoid map. And now we see what is the natural thing to do. So those two groups canonically pair with each other to, let's call it z mod p to the k, by taking the action of the functional on z mod p to the k. And I just need to give you a map like this. And I'm going to call this map omega, because I want to think about this as a root of unity. So what am I doing? I'm choosing in the endomorphism unit some element whose power p to the k is 1. So it's a root of unity. And you can reverse this process. Given such a map, I'm getting so given such a map, I get such a map, which gives me such a map, that gives me such a map. So this Fourier transform map is determined by this omega here. And it may be or maybe not be an isomorphism. If you go through the definition and unwind it, what you have here on the level of objects is a map from the coproduct of the unit, z mod p to the k times, to the product of the unit, z mod p to the k times. So this is given by a matrix of z mod p to the k times z mod p to the k, and it is exactly the Hadamard matrix that you would expect. So 1, 1, 1, 1, 1, 1, and then 1 omega squared, etc., 1 squared cubed. And I can just say that in my category C, I have a Fourier transform, or that this is a root of unity that realizes Fourier transform if I'm getting an isomorphism. So what do I learn from this? So the first thing you note that having such an isomorphism gives me an isomorphism between a finite coproduct of the unit to a finite product of the unit. And it's not hard to see that that implies that every coproduct of two things is going to be the same as the product of those two things. So it will imply zero semi-additivity. I'm going to get a semi-additive category. So this means that I can sum maps in this form. Since I can sum maps, I can consider the sum of all the powers of omega. We call this element B. And what can we say about this matrix? If I have a Fourier transform, it means that this thing has an inverse matrix, which is 1, 1, 1, 1, 1 on diagonal and 0 everywhere else. But whatever power of omega I'm going to multiply B by, it's just going to be B. So multiplying B by this matrix will make it so that all the rows are exactly the same. And that's something which is preserved by taking the inverse. So I'm going to get that all the rows in this matrix is necessarily the same, which means B is 0. If B is 0, that implies that the sum of Wi for I different than 0 is -1. So I learned that I don't only have addition, I also have an inverse. So my category is necessarily not only semi-additive, but additive. Finally, if I look at this row and the existence of an inverse here, I'm going to learn that the length of this row is necessarily has to be invertible in order to the product of those matrices to be to exist. So I also learned that, for example, if I want p to the k, 1 over p to the k is invertible, or p is invertible. So what did I learn from this very long analysis? I learned that for completely first principles, I get that if I want the existence of this very simple discrete Fourier transform, I have to be additive. I have to have p to the k root of unity. And I have to have p invertible. So indeed, the universal category in which such a thing can happen is what happens if I take z. That means I'm additive, inverting p, getting a p fruits of unity, and taking modules over that. That's if I'm taking in the world of categories. I can also do it in infinity categories, and then I'm going to take the sphere, invert p, and, well, I need to show that you can indeed add a p fruits of unity. Let me explain in a moment why that's true, and look at the modules. So that's the universal place where Fourier transform can exist, and you get it completely from first principles. So I do have to explain something about why can I add the p roots of unity to this algebra, which is the sphere p inverted. We know what it means to add p roots of unity in classical algebra, but now I want to do it in the world of spectra.
And when you said the pth root, you mean the p to the kth root.
Oh, yeah. Yes, of course. Thank you. Let me concentrate on the p fruits, just that I'm not going to carry the p everywhere or the k everywhere. It's all going to be very similar. But thanks for that. Absolutely. So why can I add the p roots of unity to spectra? Well, here's the trick. Well, if I don't do that, then this algebra does not split. It doesn't look like a product of p copies. Let's think about what happened for the case of Q to gain some inspiration. Q, taking the group algebra over Q, as we said, is not the product of p copies of Q. Rather, it's still a product of fields. You add the p fruits of unity and one copy of Q. So even though this thing doesn't split, it contains in it its splitting. That is not very surprising if we know from Galois theory. But in particular, it means that we can obtain this ring by splitting an idempotent on this commutative algebra. What is this idempotent? This idempotent has a very nice formula. It's just the sum of g over z mod p divided by p. And that's the idempotent that splits this. And this makes complete sense also in the world of spectra. I can invert inverted p, so I can take 1 over p. So, and this idempotent is exactly what splits this. Okay. So our goal is going to be to drastically generalize this very, very pedestrian way of trying to find the minimal world in which you have a discrete Fourier transform. We're going to try to generalize it in all kinds of directions and still understand what is the universal object that one can consider. But before I jump to the more generalized world, are there any questions? No. Well, I agree with your assessment that this was a bunch of triviality. So, or maybe your assessment it was completely incomprehensible, or probably both, and incomprehensible list of trivialities. So what are the ways in which we would like to generalize this? So the first instance of this kind of generalization already appeared in work of Hopkins and Lurie. And they did the following thing. So there's a certain stable infinity category, which is known as the Tn local category. In the world of stable homotopy theory, the category of spectra decomposes into different pieces of different heights, and and this is one of the heights. There's also a suppressed prime p in this notation, so it actually depends only on also on a parameter called p, which is also a parameter of a prime, and we're just going to fix the prime from now on. And in this, in commutative algebras, in this world, there's a very special commutative ring which behaves as the analog of the complex numbers. It behaves like an algebraically closed field called Morava-E theory. It's usually denoted with En to denote the corresponding number n height, and again with the prime p suppressed. And what Hopkins and Lurie showed is the following thing. So is that if you take a group algebra now, within this world, when M is again a finite abelian group, and let's analyze a P group, finite abelian P group. So we want, we're going to fix a P here. Well, this turns out not to be isomorphic to functions on M-dual, but rather function on this n-fold delooping of M-dual. So you take the Pontryagin eigendual of M, and you deloop it n times, and you get a space. And because we're working in the world of not classical algebra, but some kind of a infinity rings in spectra, we can consider functions on a space, not only on a set. And that's to get this version of the Fourier transform. And I want to emphasize this end over here, showing that it's definitely still looks very similar to what we had before, but somehow the dual object has now been delooped. So there's a bunch of generalization of this phenomena that appeared in a paper. So this is what I'm gonna quote now.
Can you maybe explain, like in one sentence, like why one should expect this EN to appear? Like, where does it come from?
The BN?
Yeah.
Let me see. Okay, I will, but I need a little bit more setup.
Okay.
So so the extension of this appeared in a joint work with Carmelli. Oh, sorry, wrong alphabetical order. Bardell, Carmelli, and Janowski. And there we show that this can be extended in several ways. So let me tell you a few of the ways that it can be extended, and then we try to analyze why does that happen. And we're going to play the game again of trying to understand what is the minimal situation in which such a thing happens. So first of all, as you know, we talked about this, the fact that if we think about here, we think about EN modules. This is a symmetric monoidal presentable infinity category. So there exists a unique symmetric monoidal and colimit preserving functor spaces. And this allows us to take this allows us to get another adjunction between commutative algebras. The adjoint to this is home from the unit. We get a define commutative algebras in EN modules, another adjunction, and functor, and this what allows us to define this group algebra construction. And you can see here that I didn't need my group algebra to be my group to be discrete. I can take a commutative group in spaces, also known as the connective spectra, and I can construct the group algebra for it. Now, we have assumed that in the previous case that our group is finite, and well, it's a finite P group in fact, and it turns out that the analog condition would be that pi star, so pi star of M, the sum of all those groups is a finite abelian. So I'm saying that there's only finitely many homotopy groups, and all of them are finite abelian P groups. And so that's going to be the context. And we can still talk about this group algebra. And the first thing that we show in this paper is that this is, in fact, extendable. So you can extend this Fourier transform into this level of generality. And you need to define what would be the generalized formula for EM-Dual. And here what it is, so denote M-Dual to be the home spectra from M to the N suspension on the Brown-Comnitz dual spectrum. So what is this operation? This is an operation in spectra that takes a spectrum, replace the homotopy groups that are Pontryagin dual, and switch their order so that so let's say it this way, pi k of M dual is then pi n minus k of M dual. That's what that means. So it's a form of Pontryagin duality that switch the order of the homotopy groups and also does a shift by n. So we see that if M is a discrete group that has only pi 0, the resulting thing is going to have only a homotopy group in degree n, and that's going to be M dual. So we're naturally going to get this space here. And that's the generalized isomorphism. Okay?
Can I ask?
Yes.
So, do you have any similar phenomenon in the case of complex K theory or elliptic cohomology, like or EMF?
You mean not completed?
Not yeah, ideally, but
So in height one, if you complete it, height one complex K theory is completed height one complex K theory is E1. So in that sense,
so they are having the geometric model. So is it possible to understand in the language of vector bundles for representation, for example?
absolutely. And yeah, I'll say something about that soon. But let me just say something about what does that say, just so we'll see that we're seeing what we're seeing. So for example, for n equals 1, you know, E1 is P complete K theory, right? So let's do the Hopkins-Lurie version. So this tells us that E1M is the same as E1 to the M dual. All right. Let's try to think what it means on I'm sorry, BM dual. So let's try to think about what does that mean for a group like Z mod P, right? So it tells us that E1 Z mod P is the same as E1 to B Z mod P. Now, the Atiyah-Siegel theorem, right, tells us that this thing is more or less the P-complete representation ring. So the P-complete representation ring of Z mod P looks like ZP adjoin X mod X to the P equals 1, generated by the character, right? And this is exactly this, right? It's I just added X mod X to the P 1. So for height 1, first of all, we see it on the level, we see it from the Atiyah-Siegel theorem. Shortly, I'm going to try to say also something about the more structured version of that. But at the very least, we see that it's compatible with the Atiyah-Siegel. Does that answer your question?
Yes, in the case of n equals to 1. I maybe possible to think about n equals to 2 case in the S two-dimensional QFT language. But
Yeah, so I'm going to get there. I'm going to get to what you can say. Other questions?
I think I was hoping that you would actually answer Andre's question. Like, I don't know what EN is, so I don't know why there should be a shift by N. But what's some of the minimal thing I need to know about EN to understand this?
So I'm trying. I know it requires a little bit of suspension of disbelief, but I'm trying to get there. This is the point is somehow that's going to shed light for us about how we should think about the end. Okay, so bear with me a little bit.
sorry, can I say a guess about it? So the TMF is level structure is so some related to the TMF is DN equivariance, and is it related to that?
In some sense, yes, but I would claim
because BN it is as if I'm using BGP instead of B2GP.
I'm sorry. No, so at height 2 we're gonna get a self-duality. It's gonna it's gonna look like the veil pairing. So if you okay, maybe that's a so on the level of TMF, what you're gonna see here is essentially something that's gonna look a little bit more like the veil pairing. It's a duality on the P torsion with itself, right? Is that okay? So yeah, but let's try to understand what is this EN, why we should expect, like what do we have here, right? So what is the data required from EN to obtain such a structure, right? So so I can play the same adjunction again. So we can look at M times M dual, and by applying all of those adjunctions, I get that I want to construct my map. I want a map from M times M dual to endomorphism of EN. If I want it to be natural, it's just going to be factored through a map from the N suspension of IQP mod ZP to the endomorphisms of EN. So this is going to bring me to the following definition. So if R is a ring spectrum, and N is a natural number, and now I have C an infinity category, and Rn pre-orientation is going to be a map from the N suspension N IQP mod ZP of R to the endomorphisms of the unit of C. I'm going to note by omega, okay? And now, if M is an R module in spectra, connective spectra, then I can consider the map from M times M dual to suspension Ni QP mod ZP R obtained by the pairing with the duality here, and then omega. And by playing the same game with the junction before, this is going to give me a map that I'm going to call the Fourier transform from the unit of C and join M, the unit of C to well, the underlying space of M-dual. And it depends on omega. And we say that omega is an orientation, not a pre-orientation, if for all m pi finite, f omega is an isomer. So for example, if I consider Z modules, also known as an abelian groups, and n equals 0, the information that I need to give you is a map from QP mod ZP to the endomorphisms of the units. So for example, if I work over the complex numbers, I have a map from QP mod ZP to the multiplicative monoids of the unit, chooses the roots of unity. And this map is an orientation. And of course, it factors through Q, all roots of unity. And if I only interested, instead of Z modules, I'm interested in abelian groups which have a given exponent, let's say a P exponent, then I can work with FP instead. And then in here, I can work only with Z mod P. So I only land in ZP. And so I get that I have all of those cases are cases of orientation. And what I'm been telling you about EN is that EN is sphere N oriented. Right? It means that every spectrum module admits this transform. But I can do this in other categories. So one can prove the following thing, the claim, to prove this is from part of the same paper I mentioned before. If C has, so let's say that C is given to me with a map. So let's say that C is given to me, and I have omega, which is a map from suspension N I Q mod Z of R to the endomorphism of the unit of C. We call it denoted by U and C star. So this is a height N pre-orientation. Now, I can consider the category of C linear categories, C mod. And I get a map from the units of C suspended to the units of D. And this is just the connected cover. Pi 0 of the units of D is going to be invertible C categories, but from pi 1 and above, I'm just going to get the units of C. So I can take the suspension of omega, and this is going to give me a map from the suspension of N Q IQ mod Z, R plus 1 to I star D. So that is a pre-orientation. And claim omega is an orientation if and only if sigma omega is.
I'm trying to parse this. D does not look like a ring to me. D looks like something else.
So this is always a category. D is a category.
And C was also a category.
C was also a category. It's a map to the endomorphisms of the unit in this category. Which is when it's a category of modules, we can think of it as just the monoids of the ring, but I want to think about it in that level of generality. And now, you know that it's important that this is a connective spectrum. So I forgot to declare something about R. Sorry. I need R here. So R needs to be a spectrum which is between 0 and N. So after I dualize it, it will still live between 0 and m. And here I need to take the n truncation of this here. Makes sense. So here's an example.
Sorry, what did you say C is? C is a category which is what? Is symmetric monodal?
Symmetric monoidal and presentable, so I can do all the colimits and limits that I want.
Thanks.
Okay, so I need to be done in 3 minutes, right? That's the email. What?
Yes.
Yes. Okay. So let's do an example.
Go better. You still have 5 minutes, I think. 5, 6 minutes.
5, 6 minutes. Even better. Okay. So let me give you an example of the kind of situation that can arise, and then we're gonna connect all this tissue back together. So C vect, for example, is Z0 oriented, right? This is what we just discussed. Which means that mod C, linear categories, is also Z1 oriented, right?
Mod C, you mean mod C vec.
Mod C vec, thank you. Mod C vec is Z1 oriented. So it admits a Fourier transform for Z modules. That's what that means. So for example, it means that if I take C vect and take the free group over A, this should be the same as C vect A dual, but with a B here. But C vect to be A dual, this is representations of A dual. Or maybe I should put the dual on the other side. It doesn't matter, it's an involution. So I'm telling you that representations of BA dual is the same as A dual many copies of C vector spaces. You know this. This is the basic fact about representation theory of abelian groups. But furthermore, the tensor product becomes the product here, which would be the convolution. So we already know this, but you can ask the question in larger generality, right? You can say, well, wait, there are more spectra than just one, which are Z modules. Generally speaking, a spectrum that lives between 0 and 1, the largest possible structure it can have is a module over the one truncated sphere. So we can ask whether or not is C vector spaces oriented with respect to the one truncated sphere? Or even more so, does this orientation extend? And the answer is no. So does not extend, but super C vector spaces is C1. So Theo, you asked me how you should think about this phenomena, right? It means that we have, like before, we didn't have orientations over Q, but we had after roots of unity. This means that you have enough roots of unity. One way to have enough roots of unity is to be algebraically closed, which is the property that supervector spaces has and the property that En has. En is like an algebraically closed object of height n. Now, you might ask then, okay, how are those things related to each other? Can we go from one of those things to another? And well, yes, you can. If you have some ring, if we have some E mod, which is Rn oriented, then you can consider mod E mod. It's going to be Rn plus 1 oriented. But you can also apply the functor algebraic K theory to decategorify. So you can take K theory of E mod. And this is going to be Rn plus 1. So there's some assumptions here that I don't have time to get into. So what do we learn from, and so another thing that you can learn from this story is, well, what are those ENs are? Those are things that get a map from K theory of En minus 1, or also if you want, it gets a map from K theory of K theory of K theory n times of mod of mod of mod of mod of complex numbers. So it's some stabilization of height n, infinity n categories that give you this map. So let me go back to the Hopkins-Lurie transform. In order to get the Hopkins-Lurie transform, you need a map from the suspension n of Q p mod Zp to the units of En. You should think of En as a decategorification of an infinity n category, such that in the top of this infinity n category, you have something like, let's say, C vector spaces. And then this QP mod ZP just goes to those roots of unity. And this is why you get this shifting, because this is a decategorification of a height n formal thing. So now you can ask the question, in the stable case, in the non-stable case, what is the universal situation in which you will have such a Fourier transform? The same way that we did in the height zero. I don't have any time to say what happens in the chromatic world, but let me just say that with Kantaro and Janowski and Mayuka and Michele, we showed that if you consider an infinity n category with Z linear Fourier transform, Z comma n Fourier transform or orientation, the universal thing that you can do is to take mod Q adjoin all roots of unity. And you do it by playing the different categorical level of each other, and then in the bottom, at height zero, the argument that I showed at the beginning. I think I'm going to stop here. Right, I'm out of time.
The questions for Robert, for the questions. No time. No further questions.
So the thing that you showed with that had C at the bottom, so something very similar to what you have there, except that had C at the bottom. Does that have a, yeah, I think, yeah, something like that. If I take the number of iterations of mod and K to be reasonably small, maybe 1 or 2, do these things have other names that might be more familiar to people in this audience?
Yeah, you can do. You can describe things like, you know, in those kind of contexts, you can consider kind of, it's kind of a Morita category, right? So you can consider algebras over C, algebras in C up to bimodal maps and things of that kind, to describe the category of C linear categories, which are small enough to contain this kind of information. Is that the kind of question you wanted? Like something like a
that takes care of the mod. Does that also take care of the K that appears in the front?
Oh, no. So the question is, what is exactly K of En minus 1, for example, or things of that kind, or, you know, even what is K theory of Q and things like that. These are hard questions, and, you know, but the important thing is that, okay, I didn't emphasize it enough, but you see, if you have a Fourier transform over some ring, and you have a larger ring, you definitely have a Fourier transform over that one, right? It's like base change. Like, it's about having enough roots of unity or enough, right? So, right, the moment that you have you can just base change both sides. So what I'm saying is that you should think about the K theory as those things like En as something that admits a map from the K theory. So it's every En linear every En-1 module give you a point in En via this map. But you know, maybe there's more information there. Maybe you did some kind of an extension or something. So this is not this. The important thing is the existence of this map. You already have the Fourier transform over this ring, but this ring is usually something that maybe in most cases you don't really have access to. There are some cases in which you do. But generally speaking, you should think about this as